Hello everyone, I'm Priyanka. I'm a third year PhD student at Georgia Tech, and in this presentation, I'm going to talk about the reliability of ferroelectric field effect transistors. And specifically, I'm going to be talking about the correlated degradation of three key reliability factors in ferroelectric field effect transistors. And these are going to be memory window closure, leakage, and read delay effects. And I'm going to talk about the evolution of these three parameters under bipolar stress conditions. And I will try to draw a correlation between all of these parameters and the role of the traps that are being generated in the interfacial layer and the ferroelectric layer of these ferroelectric field effect transistors. So before we get into the details, a little bit of an introduction to ferroelectricity. So these are materials that have non-centrosymmetric crystal structure. That is, for example, if we take a BTO crystal structure, we have the center atom that is displaced from the center towards the upward direction, and that gives us the upward polarization. And if the center atom is displaced downwards, that gives us the downward polarization. Now we can sandwich this material between two metal electrodes and apply an external electric field to switch this material between two polarization states. And that's how we get this hysteresis loop over here. Ferroelectric materials have garnered significant attention in the recent years as emerging memory technologies. And if we look at this graph over here, we have access time versus density. And at the bottom left, we have SRAM, which has high access speeds but low density. And on the other end, we have NAND, which has low access speeds but high density. And in this memory spectrum, there are gaps. And these emerging memory technologies like ferroelectric field effect transistors or ferroelectric capacitors can bridge these gaps and help enable better compute. So we have ferroelectric FETs that provide FE NAND type solutions and non-volatile SRAM type solutions. And we also have ferroelectrics in the form of capacitors as non-volatile DRAM type applications. In this talk, what I'm going to be talking about is the reliability of ferroelectric field effect transistors. So here we have a schematic of a ferroelectric FET. We have the ferroelectric layer, the interfacial layer, and the silicon. Whatever I'm going to show, the results that I'm going to talk about is all on N-channel FEFETs. So if we apply a positive program pulse to the gate of this device, the polarization will point downwards, meaning the positive polarization charges are close to the channel, making the channel easier to invert. That gives us the low VT state. Now, if we apply a negative erase pulse to the gate of this device, the polarization now points upwards, meaning the negative polarization charges are close to the channel, making it harder to invert the surface. So that gives us the high VT state. So between the high VT and low VT state is what we call the memory window. So in ferroelectric field effect transistors, there are three key parameters that change when bipolar stress is applied to the device. That is memory window, read after write delay, and the gate leakage. So I'll go into the details of what these three mean. Memory window closure is the effect that when we apply bipolar stress to the device, initially we have some memory window represented over here. And as we cycle the device with bipolar stress, this memory window closes down. And eventually the memory window goes to zero. So this is called the memory window closure effect. We also have the read after write delay effect, and that tells us that after a particular write operation is done, we need to provide a certain delay before we can read the device. So say the delay is 1 microsecond, we get a certain memory window when we measure. And as we increase the read delay, the memory window opens up and finally opens up to the value that we see and measure. We also have the gate leakage. We have a standard IGVG measurement, and we see the gate leakage look like this. And upon cycling, the gate leakage increases. So these are the three key parameters that change under bipolar stress conditions. And I'm going to show you that these three parameters, the degradation of these three parameters are correlated, and these are correlated to the traps that are being generated in the FE and IL layers. In order to do this, this is the device that we've fabricated. We have the standard process shown over here. We have a 10 nanometer HZO layer that is ferroelectric. And here we have the standard characteristics. We have memory window versus voltage, and we see that we have about 2 to 2.5 volts memory window for 5 volts write voltage. Here we have just a DC IDVG characteristic. So to perform these set of measurements, this is the measurement schematic. We have bipolar stress, often interrupted with a read operation, and the read operation is expanded over here. We have a pre-polarization pulse that sets the device to one fully polarized state, and then we have the negative erase pulse and the positive program pulse. And we vary the delay, that is the read delay, from 10 power minus 4 seconds to 10 seconds in each case where we measure the memory window. So now let's get into the details. Now, if we apply bipolar stress and intermittently measure the memory window with certain read delays, during the bipolar stress conditions, the key thing to note is that there is going to be polarization switching. In each pulse that is positive and negative, we will see polarization switching. Now, let us look at the evolution with cycling. So what's commonly seen is that upon bipolar stress, the memory window closes down, and that's what we see over here. The high VT and low VT state are separated initially, and with bipolar stress cycling, it closes down to 0. Now, if we take a closer look at cycle 1 and vary the read after write delay, what we see is that the memory window opens up as we increase the read after write delay, as seen over here. So what's actually happening here is that upon applying a particular pulse to the device, we have certain number of electrons appearing at the IL interfacial layer, and when we provide only a very small read delay, these all electrons that are screening the polarization are there, and that leads to a reduced memory window that we observe. But when we increase the read delay time provided, some of these electrons now go back to the channel, and that leads to lesser screening of the polarization. Now that leads to an increase in the memory window that we observe. So as we provide more read delay time, the memory window opens up. Let's look at what happens when we perform the same read delay measurements at 10 power 4 cycles. That is, we've applied 10 power 4 cycles, and now we perform the same measurements. So again, as we cycle the device, the memory window opens up. But what we see is that the amount the memory window opens up to is much lesser than what we see earlier. That is, the recovery due to increasing the read delay has reduced. Along with it, we also see that the VT has shifted towards the right. Now, again, after 10 power 5 cycles, we see the same effect. That is, as we increase the read delay, the memory window opens up. But again, the amount of recovery due to the increase in the read delay has reduced. Initially, we saw a 0.55 increase in the memory window, that is LVT, when we increased the read delay, but after 10 power 5 cycles, the recovery due to increase in read delay has reduced. So what's now happening here is that initially we have some read delay, and there are a lot more traps that are present in the interfacial layer screening the polarization, which explains the shift in the VT and shift in the closure of memory window. But now, as we increase the read delay, lesser amount of these traps are able to move away from the interfacial layer. So that's leading to the reduced recovery of memory window as we increase the read delay. So here's all of those results put together. Initially, we had a 0.55 volt recovery in the memory window as we increase the read delay, but as we cycle the device, this recovery has reduced. So there are two things happening here. One is that the LVT has significantly shifted upon application of bipolar stress pulses, but along with that, the recovery of memory window with read delay has reduced. So initially we have fast traps that are going away from the interfacial layer and leading to the opening up of memory window. But after we cycle, these traps are not able to recover and lead to a lesser change in the memory window as we increase the read after write delay. So here's the same thing plotted in a different form. In cycle 1, we have large recovery of memory window, but as we cycle the device, the recovery reduces. And over here we have the shift in the VT as we cycle the device. So there are new traps being generated that are shifting the VT, and these traps are also slow traps that are unable to recover after cycling the device. Now, we need to be able to deconvolute the effects of polarization switching and just simple voltage stress. In order to do this, we perform the same read after read delay measurements but with unipolar stress cycling. Here we have negative unipolar stress applied, and the key thing is that when we apply these negative unipolar pulses, there is no polarization switching occurring with cycling. And now we have the same read measurements with the pre-pole pulse and the erase and the program pulses with different read delays. So here we have the evolution of the memory window with unipolar cycles. We see that the memory window doesn't close as much as it did in the bipolar stress case. We still do see some VT shift, but it's not as significant as the bipolar case. Now, if we look at the impact of increasing the read delay, we see that initially there is some amount of recovery with read delay, but this doesn't change with cycling. If anything, it only increases a little bit. So over here, we don't see the lack of recovery with read delay as we saw in the bipolar stress cases after cycling. Similarly, with positive unipolar stress, we see the same results. We see that there is some recovery with read delay in the low VT state in the initial state, and this does not change even after cycling. So here's a summary of the results over here, and we see that what's actually happening here is that initially, like in the bipolar case, there are some electrons screening the polarization, and these go away to recover the memory window with increased read delay. But after cycling, we have some traps generated, which results in minimal shift in VT, but these traps are fast traps and recover as we provide the read delay, unlike in the bipolar stress case. So if we put all of them together, we see that in the bipolar stress case, we have polarization switching, and that leads to increase in the low VT state, that is significant VT shift upon bipolar stress cycling. And this also leads to a reduction in the recovery of the VT after we cycle the device. Initially, we have large recovery, but after cycling, the recovery significantly reduces. But in the case of the unipolar stress cycling, we do not have polarization switching, and we see that there is very minimal VT shift in both cases, and we see that the recovery of memory window with read delay does not change with cycling, indicating that there are minimal amount of traps being generated in the unipolar case, and these traps are likely fast traps that do not affect the read delay effect that we see. Now we move further and look at the leakage of the device under these three conditions. So we perform IGVG measurements, DC IGVG measurements with bipolar stress and unipolar stress. In the bipolar case, we see that as we cycle the device, the leakage begins to increase. But in the unipolar stress case, there is very insignificant increase in the leakage as we cycle the device. This is the case in both positive unipolar and negative unipolar cases. And the interesting thing to note here is that until 10 power 4 cycles in the bipolar stress case, the leakage does not increase significantly. But post that, the leakage starts to jump to much higher values. The thing is that at 10 power 4 cycles is when we see the memory window closure happening. So if we look at the values plotted over here note that the y-axis is in a log scale, and as we cycle the device under bipolar stress until 10 power 4 cycles, the leakage remains below 1 microampere per centimeter square, but after memory window closure, it shoots up to about 2 orders in increase in the leakage value. But in the unipolar cases, both positive and negative, this leakage remains low throughout the cycling. So let's look at what's happening here. We see that as we cycle the device, the leakage roughly remains the same, indicating that the new traps being generated that we saw that leads to memory window closure do not contribute to the leakage current. So the dominant mechanism of leakage in ferroelectric FETs through the HZO is trap-assisted tunneling. So as we cycle the device, a lot of the traps are being generated in the IL layer, which do not contribute to the trap-assisted tunneling leakage. But once the polarization is fully screened, the electric field now shifts to the HZO layer, leading to an increased trap generation in the heads, which now leads to an increase in the leakage. So initially we have trap generation localized to the IL, which leads to both the memory window closure and the read delay effects that we saw. And post memory window closure, this electric field now shifts to the heads layer, leading to an increased trap generation rate in the heads. To further confirm this effect, we performed simulations to increase the traps in the SiO2 layer and increase the traps in the heads layer independently. So we see that when we increase the silicon dioxide traps, the leakage does not increase. But when we increase the heads traps, the leakage begins to increase, confirming that the effect that we see, that is until memory window closure, there being no significant increase in the leakage, is primarily due to the traps being generated being localized to the IL layer and not contributing to the leakage. So now let's put all of this understanding together. We saw that as we cycle the device under bipolar stress, we see memory window closure. That is, the low VT shift under bipolar stress indicates increase in electron trapping. Now that's what we observed with memory window closure. Now we put that along with the read after write delay effects. We see that the traps that are generated that close the memory window are also slow traps that lead to a reduction in the read after write delay recovery of the memory window upon bipolar stress cycling. And along with that, we looked at leakage, and we saw that the traps that are being generated that are leading to these two effects are mainly localized to the IL layer of the device. So looking at all of these results together gives us a full understanding of the mechanism of degradation of ferroelectric field effect transistors. Bipolar stress cycling, that is polarization switching on each cycle, leads to accelerated trap generation case where we see significant increase in low VT state leading to memory window closure. And these traps that are being generated are slow traps that do not recover even after providing a read delay. And from the leakage measurements, we saw that all these traps are localized to the IL layer of the device, leading to insignificant increase in the leakage of the device. Thank you for your attention, and I would like to acknowledge and thank our sponsors for supporting this work.